Okay, we're going to begin Unit 4 in our geometry class, which goes along with Chapter 4 in our current textbook that's about congruent triangles. So we have three big ideas that we're going to be focusing on in this unit. The first is classifying triangles by sides and angles, and there's emphasis on that in this video. We also, for the remainder of the unit, will be proving that triangles are congruent, as well as using coordinate geometry to investigate triangle relationships. So in other words, we're going to be applying our distance formula and midpoint formulas. So you have your Cornell note sheet, and you'll be writing on the right-hand column the information that's contained in this video. And then if you'll notice in the left-hand column, there are headings as well as page numbers where you could find this in your textbook if you needed further investigation. So the basics that you already are aware of, we just want to remind you, are how we can classify triangles by sides. And when we classify by sides, there are three types. We have scalene triangles, in which no sides are congruent. We also have isosceles triangles, in which at least two sides are congruent. And it is important that you emphasize and recognize that it says at least. Okay, so at least two sides are congruent. And then our equilateral, in which three sides are congruent. And because the definition for isosceles recognizes at least two sides being congruent, that means that every equilateral triangle is also isosceles. So you could think of your Venn diagram, in which we did the two circles, one inside the other. And your isosceles triangles are in the big circle, and your equilateral are inside the little circle. So not every isosceles would be equilateral, but every equilateral is considered isosceles. Moving on to classifying triangles by angles. Now we have four types. So we have acute triangles, in which there are three acute angles. We have right triangles, in which there is one acute angle. We also have an obtuse triangle, in which we have one obtuse angle. Classifying as an equiangular may be new to some of you, but an equiangular triangle is very similar to an equilateral in that all the angles are equal. So you should be able to figure out if we have 180 degrees in a triangle, that would mean that each angle is 60 degrees. Another aspect of this course that you want to be able to recognize is looking at an angle and determining if it's an interior or an exterior. And we've talked about this a little bit with the last unit, but we really want to focus right now on the fact that we're looking at a triangle. So our interior angles are those that are inside, and they're shaded in red. And then our exterior angles are those shaded in blue. It's important to recognize that the interior and the exterior angles form linear pairs. So let's look at the example that we have in your notes and see if we can list the interior angles in this example. So they would be, excuse me, that would be 1, 2, and 3, and our exterior would then be, my airliner's really off, would be 4, 5, and 6. And again, I apologize for that, having a little technical difficulties with the airliner. And notice 1 and 4 are a linear pair, 2 and 5 are a linear pair, and 3 and 6 are also a linear pair. A theorem, our first theorem in this chapter, is something that's not new to you guys, but it's the fact that the sum of the measures of the interior angles of a triangle is 180 degrees. So we've used this, but again, we just want to recognize and give it a name, that it's called the triangle sum theorem. And you can pause the video and draw an example of your own. Something that will be new for you guys is looking at this exterior angle theorem. And what that is telling us is that the measure of an exterior angle, so here we are, example 1. This exterior angle is equal in sum to the measures of the two non-adjacent interiors. So that would be these guys over here. Okay, so again, this exterior angle is equal to the sums of the two non-adjacent. So the exterior has one adjacent interior and two non-adjacent interiors. So let's see if we can run through this example. We want to find the measure of JKM. That would be the exterior angle. So we start by writing and solving an equation to find x. So we said that the exterior angle is equal to the sum of the two non-adjacent. So that's where we're applying the exterior angle theorem. And then we're going to work through our algebra, and we're going to solve for x. So we're going to add 5 to the right, subtract x to the left, and we get that x is 75. But as you know, we're not done. We have a second step. That second step is to substitute x with 75. So we have 2 times x minus 5, which is 2 times 75 minus 5, which is 145. So our final answer is the measure of JKM is 45 degrees. Moving along to our corollary. And a corollary is a statement that can be proved easily using a theorem. So this is your first introduction to a corollary. And corollaries are very useful. So the corollary states that the acute angles of a right triangle, so if if C is the right angle, then A and B are the acute angles. They are complementary angles. Their sum is 90. Recall the triangle sum theorem says there's 180 degrees in a triangle, and a right triangle contains one 90-degree angle. So 180 minus 90 leaves 90 degrees left over for each of these two angles. And we know that our definition of the definition of complementary angles is the sum of two angles out of the 90 degrees. So here we have an example in which we have a tiled staircase, right? And the tiled staircase forms a right triangle. The measure of one acute angle in the triangle is twice the measure of the other. So let's find the measure of each acute angle. So first we want to do is to be able to sketch a diagram of the situation and let the measure of the smaller angle be x and the measure of the other angle be twice x. Okay, so I'll review in words what I just said. We're sketching the diagram. We're letting one angle be x, that would be the smaller, and the larger angle be 2x. From here, we can use the corollary to set up and solve an equation that 2x plus x equals 90. And then we can solve our algebraic equation, and we get a result that x is 30. If x is 30, then that means we should be able to substitute back in and find out that this measure is 30 and this measure is 60. Alright, so that wraps up section 4.1, which is a lot of review. So we're going to move on to section 4.7 in your book, which begins on page 265. And while we were talking about isosceles triangles in 4.1, we want to be able to point out in this section, because this section is strictly about isosceles and equilateral triangles, we want to point out the parts of an isosceles triangle. So you may need to add this part into your notes if you're not aware of how these are labeled. So the two congruent sides are the legs. The non-congruent side is the base. The vertex angle is the angle that is formed by both legs. Therefore, the remaining two angles that are adjacent to the base are called the base angles. So we have something called the base angle theorem. And the base angle theorem states, and if you notice the hypothesis, if two sides are congruent, so I have two sides are congruent, then the angles opposite those sides are congruent. So I go from sides being congruent to knowing opposite those sides are angles that are congruent. The converse of that theorem, so that means our conclusion became our hypothesis, states we know these angles are congruent, so now we can conclude that the sides opposite them are congruent, and therefore I must have an isosceles triangle. So here's a guided practice problem. I want you to make sure you draw the image and answer the questions, and then you can continue in the video with your notes. Okay, now that you're done guided practice 1 and 2, let's look at the corollaries that are for the base angle theorems. All right, so the corollary to the base angle theorem states that if a triangle is equilateral, then we can conclude that it must be equiangular. And the converse just says if we know it's equiangular, that means we can conclude that it would be equilateral. So you have guided practice problems 3, 4, and 5. So what I would like you to do is complete the guided practice problems 3 and 4 that are shown on your screen. When you're done that, I want you to go ahead and you're going to read over example 3. If you would like to go ahead and copy example 3 down in your notes, that is okay. It's just another example that may be able to help you with the next guided practice problem. So we're not going to worry about example 4, so you can ignore that in the Cornell notes. So here in example 3, you have to find the values of two variables. Make note that KNL is an equilateral triangle. Well, it's equiangular, so the corollary tells us it's equilateral. Just like triangle LNM is isosceles because we have the converse of the base angles theorem that says if two base angles are congruent, then the sides opposite those are congruent. So you're going to go through and use triangle KNL to solve for Y, and let that help you solve for X in triangle LNM. So here's example 5, and you can go ahead and pause the video, this is the end, and get this problem finished. And when you're done this, I expect that you're going to go through the notes summary, and there's 6 questions, and I want you to answer all those questions. Alright, I'll see you in class tomorrow.